18.1, here we're going to talk about double integral over rectangle. Now, in the past, we have single integral, right? Okay. Do you guys remember what does it represent? So you have this single integral that you had before. Integral of a function, and x here go from a to b. Geometrically, what does it represent? It is related to what? Well, if it's a positive continuous function, f, then this integral here actually represents the area under this curve, right, from a to b. So this is what this integral here represents. Now today, we have this double integral. So we have this double integral over here. And we're going to find out geometrically what does it represent. So keep that in mind. Okay, let's think about it. I'm going to review the answer to you later on and we think about it. Now let's review the definite integral first. Okay. How do we get the definite integral? How do we get this definite integral over here? The way we did that is we use a Riemann sum, right? When we try to find the area under a continuous curve like this, and what we did here is, what did we do in the past? We slice it into n slice, and then for each slice, we're going to approximate each slice using a rectangle. And then we sum up the area of those rectangles. And as the n here go to infinity, which means if we divide that into finer and finer rectangle, the sum of those rectangles will be approaching to the area under the curve, right? This is the Riemann sum that represents the total area of those n rectangles. The xi star, okay, so what is this xi star? This xi star over here, look at the picture here. Those xi star are just any arbitrary point in each subinterval. So for example, you divide that in n subinterval, the first subinterval, you pick a random point, arbitrary point. And then you take the y coordinate of that point as a height, and you take the width of this rectangle. So width times height gives you the area of this rectangle. So that's how you got this. How you got this f of xi star times delta x. And you sum n of them up, right? We have n rectangle. So I go from 1 to n. And if you slice this into finer and finer pieces, and as n go to infinity, then the sum of those rectangles will approach to the area under the curve, right? So that's how we got this definite integral, and it represents the area under the curve if f is a positive function, right? Now, today we're going to do something similar to this. Now, over here, what do we have? We have a rectangle, okay? So this rectangle over here is, okay, so let's look at the picture here. It's going to be, the x here will go from A to B, the y will go from C to D. So that's why they put down like this. So that is going to be A comma B cos C comma D. And that's the rectangle. So today we just focus on when this region on this xy plane here is a rectangle. In the future, we're going to generalize it to other shapes. So in this section, we focus on this as a rectangle. The graph of the function is going to be like, is this surface over here. So imagine that this is like maybe is the cloud in the sky, and this is the shadow on this xy plane. Another way, you can also think about this. So you can have to think about this. This is the umbrella. So that is the surface over there. And but of course, down over here, the region is not a rectangle. But imagine it's a rectangle down there. Then what happens here is, if we try to find the volume under this umbrella to the ground, okay, imagine that, we are going to use something called double integral. Okay, so how do we do that? To do this, we're going to just use Riemann sum again. In the past, we divide the interval into n subinterval. Okay. Now this time we're going to divide this rectangle into subrectangle. How do we divide that into subrectangle? Let's look at this picture. So here is how you divide that rectangle into subrectangle. So on this x-axis, okay, x go from A to B, you divide that into m subintervals of equal with delta x. Along this y direction, you also divide that into n subintervals. And now you're going to get a partition of this rectangle into small subrectangle. So it's a very similar idea as the one that we did for definite integral. And what you do over here is you're going to pick a random point inside each subrectangle. And let's call that point xij star. Okay, if you can see that. Okay, that's called xij star, comma yij star. It has two index because that point here has the x coordinate and y coordinate. So it's called xij star. So basically it's on the I column and also along this j row, right? Okay, this is the one. So we pick this arbitrary point inside this subrectangle. And what do we do? Let's look at the picture. And we are going to take this point and look at the function value at this point, which is the height of this, right? Now we're going to use this height to kind of represent or approximate all those function value inside this subrectangle over here. And what are we going to do? We're going to take the base area over here, multiply by this height. When you use the base area here times this height, that's going to give you the value for this rectangular box, right? This rectangular box over here. And we're going to use that to approximate the area under the surface when the projection of that is this subrectangle over here. Okay, do you get the idea? Now, it might be good to see the animation. So let's do the animation. Okay, now this is the surface, right? It's the graph of the function above that rectangle on the xy plane. Now, our goal here is to try to find the value of the solid that's under this surface and above this xy plane. So we project the surface onto the xy plane. It should be a rectangle over here. And now you partition the rectangle into subrectangle. And now you pick one of the arbitrary subrectangle. Let's just pick this one. And you pick a random point inside the subrectangle. Okay, so this is xij star, yij star, and the z coordinate of that point should be 0, right? It's on the xy plane. And now you're going to use this function value at this point as the height. And then you're going to have this rectangular box, vertical rectangular box over here. And you're going to use this value over here to approximate the area under this part of the surface above this subrectangle. Okay, do you guys get the idea? Okay, so this is, how do you get the value for this subrectangle? You're going to use what? This height, which is the function value over here, which is f of xij star or yij star, and then times what? Times this area, right? This subrectangle area. So base area times height give you the value. Now going back, and you can see if you use those subrectangle, right? And then you use the height for those each random point in each subrectangle as the height, okay? And you get you sum up all those rectangular boxes. So this is how it looks like, right? Okay. Now, how do you represent the sum of all those rectangular boxes? You need this double summation right here. So remember, for each rectangular box, it's going to be the function value at that random point, right? At that random point in each sub-rectangle, which is f of xij star and yij star. This is the function value. Think about that as the height, right? As the height of that box. And then delta A here is the area of that subrectangle. Okay, so base area times height give you the value for one rectangular box that we have. And how many those rectangular box we have? Well, from A to B, we divide that into M subinterval. And from C to D, along the y direction, we divide that into N subinterval. So that's why here we have I go from 1 to M and J go from 1 to N. So we have a double summation right here. The delta A, remember, is the area for each sub-rectangle. Okay. Any question here so far? Okay. Now we're going to do the similar trick as in the past. We're going to take this M and N go to infinity. And what does it mean? That means that we're going to divide each, we divide that into finite and finite subrectangle, okay? So M and N go to infinity. As M and N go to infinity, then this double summation is going to be approaching to the value under the function. Okay, think about that. If it's a positive function, so it's a value under the surface of the function, right? Under this umbrella right there. Okay. So here I actually put this up. Okay. So the limit of this double summation over here is this double integral. And how do you represent this double integral? You just replace this 2 by x and y, and then delta A here by dA. And you integrate this over the region R, where R here for rectangle. So that's why here is called R. So that's the rectangle that is down over here. So what does this double integral here represent geometrically? Well, think about that as, if it's a positive function, think about that as the value under the surface. Okay, so let me put it up. So that should be the value under the surface. Now let's compare this with what we have in the past. This one over here. This is the single integral, right? The single integral here is the limit of this Riemann sum. Okay, this is a double Riemann sum. This is a single Riemann sum here. And what does it represent? It represents the area under the curve.
If f is a positive function.
Okay. Now the answer is revealed. Now this single integral here, you can think about that. It represents the area under the curve. The double integral represents the value under the surface.
If function f is a positive function.
Now, what does it mean a function is integrable? Okay, if the limit in this one, in this over here, exists, so then the function is integrable. So when this double integral here is equal to a finite number, then we call that function is integrable. So now we can actually make things a little bit simpler. Instead of picking a random point here in each subinterval, we can actually pick this. Okay, let me make it larger. We can pick this upper right corner in each subinterval. So the upper right corner here has x coordinate to be xi, y coordinate to be yj. So this point here will be xi, yj. So you don't need to put the star there anymore. The star here just represents an arbitrary point in this subinterval. But if you pick the upper right corner, then you don't need to put a star there. Okay, so that is the x and y coordinate of that point. And we can pick that point as the random point in this Riemann sum. Okay, now this double integral is the limit of this double Riemann sum right here without the star. Okay, using the upper right corner here. And as you here, just we iterate this. When the function is a positive function, then that represents the value. So it's called double Riemann sum. This one here, double Riemann sum. How about we try to use some example to understand this? So the first example over here is
Estimate the value of the solid that lies above the square 0,2 cos 0,2 and below the elliptic paraboloid z equal to 16 minus x squared minus 2y squared. We're going to divide the region R into 4 equal squares and choose the sample point to be the upper right corner of each square. Sketch the solid and the approximating rectangular boxes.
Let's take a look. So the rectangular region is this region, 0,2 cos 0,2. So x go from 0 to 2, y go from 0 to 2. And what are we going to do? We divide that into 4 sub-rectangles. Each one has equal width and height, okay? Then you see that what happened here, they ask you to use, in each sub-rectangle, you pick a point. This time they say, oh, let's just take the upper right point, upper right corner right here. So we pick the upper right corner in each. So this one will be 1, 1, 1, 2, 2, 1, 2, 2. And we're going to use a function value at those points to as the height for those rectangular box. And the way that we do it is like this. So we take the function value f at 1, 1, which is f11. And then we're going to multiply that by the area of this subrectangle. Take the function value over here times the area of the subrectangle, etc. And we have 4 of them. And since each subrectangle had the same area delta A, you can actually just put the delta A outside and just add up the function value over here and times delta A, right? And then you do the calculation, turn out to be 34. So what does it mean? That means the volume
under the surface
could be approximated by the sum of these 4 rectangular box, and 34 will be one approximation. But that approximation is actually an underestimate or overestimate of this value under the surface. Overestimate or underestimate? Underestimate, right? Because you have space right here. Because the function is actually above those
boxes.
So underestimate. Okay, good. And now, as you can see that if you make those rectangular subrectangle to be finer, as actually approaching to the volume under the surface, right? Okay, good. Okay, let's look at another example, example 2. This time we have, again, in this section, we focus on the region is going to be a rectangle. This rectangle here, x go from negative, let me see, x go from -1 to 1, and then y go from -2 to 2. So imagine you have a rectangle down on this xy plane. And what are they looking for? They're looking for this integral, this double integral of this function over this rectangular region on the xy plane. Now, how do we do this? Well, we can actually, if you try to use those Riemann sum, it will be hard, right? However, because notice this function here. This function here is a positive square root. So it is a positive function. So it is going to be above the xy plane. So we can interpret that this double integral here as the volume, right? As the volume under the surface and above this xy plane, right? So basically we try to find the value of this. But if you're looking at this is y equal, so what do you have here? Okay. You have this z, right? This one here is a z. This is the function value, f of xy. right? And you can also think about it as a z, right? Z is equal to square root of 1 minus x squared. And if you square both sides, you're going to get z squared equal to 1 minus x squared plus z squared equal to 1. Then on the xz plane, what kind of curve do you have on the xz plane? It is a circle, right? It is a circle. However, here, because z is the positive root of this, so z has to be what? Greater than or equal to 0. So that is going to be correspond to this. It's going to be on the xz plane. It's going to correspond to this half circle right here, right? Agree? Okay. And now, what happened over here is the graph for this is going to be a cylinder, remember? Okay, and this is just on the xz plane, but then imagine that it's going to go along this direction, the y direction, because y could be any number. So go along the y direction, then you're going to get a surface like this, right? And each one of this will be half circle like that. Okay. Now, because the y here is restricted from actually -2 to 2, then you get this part of the surface right here. Okay. But we know how to find the value for this kind of solid, right? Okay. We can just use, what can we do? We can use what? Base area times height, right? What's the base area over here? Okay, let me highlight that. So let's try to find this base area. Well, this is half a circle, right? Okay, so that is what? What's the radius for this circle? 1?
1.
Yeah, 1. So the area for this circle will be just pi, right? Pi r is 1, right? So it is pi times 1 square, and it is half a circle. So this will be just half pi. Okay, so that is going to be, this one here correspond to this right here. Okay, the area over there. And then we can multiply this base area here by the height. The height for this is y go from -2 to 2. So the height for that will be 4, right? So this is like, because y go from -2 to 2. So the height is going to be 4. So that's why this double integral here, when we interpret that as the value under this positive function,
Under this surface,
we actually could find out this double integral without doing those integration method. Okay, just interpret that as the value.
under this surface.
Just do a quick animation. Now let's see the process. Okay, so now we have x squared plus z squared equal 1 on the xz plane will be a circle. But on 3D, this is going to be a cylinder, remember, right? So it's going to be a cylinder. So y could be any number. So you extend it along the y direction, you get cylinder. And then the y go from -2 to 2, okay, because it was given. So you restrict that from -2 to 2, y go from. And you only take half of it, half of this cylinder, because this is the positive root, remember. So you only have z is greater than or equal to 0. So only have this half cylinder. And now you just need to find the value for this cylinder, okay, which we already did. Okay.